In this video, we will introduce Schrödinger equation. Specifically, we will introduce time-independent Schrödinger equation. The equation looks like this. It has negative h bar square over 2m times del square, the differential operator, plus v is a function of position. That whole thing is multiplied to a function psi, and that is equal to a scalar constant e times the same function psi. The problem is essentially defined by the operator inside the bracket, and that operator is called Hamiltonian, and we denote Hamiltonian operator typically using capital letter H. As you can see, the Hamiltonian operator consists of two terms. First is the term that contains the differential operator del square, and that, as you will see later, represents kinetic energy. And the second function v is the potential energy. Now, the task is to solve this equation to obtain the function psi and the constant e simultaneously. In algebra, this type of problem is called eigenvalue equation, and the solution of the eigenvalue equation is called eigenvalue. The scalar constant e is called eigenvalue, and the function psi is called eigenfunction. Because Hamiltonian operator represent energy, as I just mentioned, sometimes we call e energy eigenvalue and psi energy eigenfunction. Now we're going to look at the various aspects of Schrödinger equation, time-independent Schrödinger equation, by considering a very simple example, namely one-dimensional infinite potential well problem. One-dimensional infinite potential well is defined by this potential profile V of Z, which is 0 inside the well between 0 and L. L here is the width of the potential well, and then the potential is infinite outside. Now, outside the well, if an electron is to exist in this region, then the energy must be infinite, which is unphysical, and therefore we require that electrons cannot exist outside the potential well. And because the wave function represents probability of finding an electron, we require the wave function to be 0 outside the potential well. Inside the potential well, because V potential energy is simply 0, the time-independent Schrödinger equation becomes this simple second-order differential equation, whose solution is given by sine and cosine function. So the general solution to our Schrödinger equation is given by the sine and cosine function. The parameter k inside the sine and cosine function is given by the original differential equation. In our case, k is square root of 2me divided by h bar squared. Now, we need to determine the constant a and b, and also this unknown constant e, which is our eigenvalue. Now, how do we determine that? We impose boundary conditions to determine those values, and the boundary condition is given by the requirement that the wave function is continuous across the entire problem. So specifically, we require the wave function to be continuous at the boundaries of the potential well. Outside the potential well, we require the wave function to be 0, and therefore, at z equals 0 and at z equals L, our wave function, sine and cosine, given by the sine and cosine function, should be 0 in order for the wave function to be continuous across the entire space. Now, the first condition, psi of z equals 0 to be 0, that condition gives us that the constant b multiplied to this cosine function to be 0, because cosine function cannot be 0 at z equals 0. So in order for the wave function to be 0 at z equals 0, we need to get rid of the cosine function, and then that means the constant b multiplied to cosine function is 0. The second condition, z equals L, the psi is 0 at z equals L, gives us a condition for a constant k here. And in order for the sine function to be 0 at z equals L, the k constant here should be an integer multiple of pi over L. Specifically, we can write this wave function now like this: a sub n constant times the sine function. Now we spelled out k as n pi over L. So that's the argument going into the sine, and that is our wave function. Notice that we inserted subscript n to both our wave function and the constant n here, constant a here, in order to indicate that there are multiple values of n that is possible. N could be any integer. Now, because condition for k is given here, and k is related to the energy eigenvalue E according to this equation, now we can solve this equation for energy eigenvalue E sub n, which is h bar squared divided by 2m times n pi over L quantity squared. So this is our energy eigenvalues for the 1D infinite potential well problem. Once again, this n here is an integer. Now the last task is to determine the constant amplitude of our sine function, capital A sub n, and this can be determined by imposing the normalization condition. The normalization condition, if you recall, was to integrate absolute value square of the wave function across the entire space. That integral should be equal to 1. So that's the condition for us. And if you do this sine square integration, then you will find that the constant a sub n is simply given by square root of 2 over L. Now, because the condition, normalization condition, give us a condition for absolute value of a sub n, we are free to add any arbitrary phase factor with a unit modulus, e to the I theta, and theta could be any number, any real number. It doesn't really change anything because the physically meaningful quantity, once again, is the absolute value squared of the wave function. So there is a freedom given to us, or there is a certain inherent level of uncertainty with the phase factor. And so typically we choose a phase factor that is the simplest and most convenient for us. In our case, we simply choose the phase factor here to be 1 so that a sub n constant is a real number. So we can summarize the 1D potential well problem as shown here. Here is the wave function psi sub n given by the sine function, and here is the energy eigenvalue E sub n. We restrict the integer n to be a positive integer because when n is equal to 0, your sine function becomes 0. So in that case, your wave function is 0 everywhere, both inside and outside, which means that there is no electron. So that is a meaningless case. So we exclude that. And also, the negative integer n simply gives you the same function, same sine function, with a negative sign, minus sign out in front. And because of the function is the same, except for a constant multiple, those two wave functions are considered identical, and those are considered the same quantum state, and therefore the negative integer simply gives you a duplicate same state that is already represented by a positive integer n. So we only count, we only consider the cases where n is a positive integer. So the lowest energy state here is represented by n equals 1. And then the next higher energy state is n equals 2 and n equals 3 and so on and so forth. There are a few non-classical behavior we can notice. First, there is a discrete set of allowed energies. In other words, energies are quantized. This is a very important and uniquely quantum mechanical behavior. The energy being quantized is the phenomenon from which the name quantum mechanics is derived, obviously. And the lowest energy, E sub 1, is not zero. This non-zero lowest possible energy is often called the zero-point energy. And this has a very important ramification in many areas of physics. And also, lastly, particle is not uniformly distributed throughout the well. As you can see, the wave function is described by sine functions, which has antinodes and nodes. And therefore, if we take absolute value square of the wave function, which represents the probability of finding an electron at certain positions, and they are not uniform. So the electron distribution inside a box, inside a potential well, is non-uniform, which is, once again, is a non-classical behavior. A well-known example of this potential well problem can be found in a semiconductor nanoparticle often called quantum dots. And in quantum dots, first of all, the band gap energy is generally larger than the bulk semiconductor, and the band gap energy depends on the size of the quantum dot. And this is related to the zero-point energy that we just observed in the 1D potential well problem. And you must have noticed that the zero-point energy depends on the width of the potential well, or the size of the nanoparticle in the case of quantum dots. So because of these varying band gap, when you shine UV light onto these semiconductor nanoparticles, they emit various different color corresponding to different wavelength, corresponding to different energy. And the electron distribution also is non-uniform inside the quantum dot, and the electron tend to aggregate towards the center of the nanoparticle and has a less probability on the surface and outside. And this also is consistent with the sine functions that we obtained as a wave function of the 1D infinite potential well problem.